So hi everyone, and welcome to the ATMCS series. The first speaker today is Siddharth Vishwanath, and the title of his talk is Statistical Invariance of Betti Numbers in the Thermodynamic Regime.
All right, do I go now?
Yes.
Okay, perfect. Thank you. I'm Siddharth from Penn State, and I'm a third-year PhD student. And this talk is sort of based on joint work with Bharath Sriperumbudur from Penn State, along with Kenji Fukumizu and Satoshi Kuriki from the Institute of Statistical Mathematics. And the general outline of the talk is I will sort of spend a little bit of time talking about the probabilistic setup and the statistical setup for the problem. Then I'll describe what we mean by statistical invariance of Betti numbers. And then towards the second half, I'll just describe how we can construct families that admit invariance and how we can verify whether a given family of distributions admits invariance or not. Okay. So a common problem in statistics is to understand the structure of the underlying data generating mechanism. And here's an example from the 1970s from Anscombe, where conventional quantitative summaries are insufficient to infer the underlying structure of the mechanism. So if you look at it quantitatively, they all look identical, but visually they're very different. And in the present day and age, data generating mechanisms often lie on lower dimensional structures embedded in much higher dimensional spaces. And the tools from algebraic topology are very useful in the scope of statistics for understanding the structure of the data through what is known as exploratory data analysis that was advocated by Tukey, who interestingly was a topologist who made a lot of fundamental contributions in the world of statistics. So the quantities that we're interested in are the Betti numbers. I won't engage in the superfluous task of having to describe Betti numbers to an audience of topologists, so I'll just leave it at this. But I'll spend a little more time on describing the probabilistic structure in a little more detail. So we're given some random points sampled from a probability distribution defined on any metric space, and more specifically, it's a Euclidean metric space. And for a radius r, we place balls of radius r around the sample points, and we construct some simplicial complex, which is a random element which is measurable with respect to this n-fold probability measure. And the topological summaries themselves are random elements that live in a suitable summary space. So examples that have been studied in this random topology setting include the Betti numbers, the Euler characteristic, and even persistence diagrams. And the seminal results that have emerged over the last decade shed light on the behavior of these random topological summaries, particularly in the asymptotic setting, by establishing their behavior in the law of large numbers or the central limit theorem setting. And the survey paper by Bobrovsky and Kale sort of they exemplify the wealth of literature that has emerged over the last 10 years in this area of random topology. So the limits are highlighted in red because it turns out that the asymptotic behavior of the random topological summaries qualitatively differs as the rate at which the radii of the balls shrink to zero as n goes to infinity. So if it decays very slowly, then everything is connected, and this is known as the dense regime. If it decays too fast, then everything is disconnected, and it's called the sparse regime. And technically, within the sparse regime, there are different tranches which characterize the behavior of simplices of different dimensions. But the take-home message is, if we look at the highest dimension simplex we can construct on the underlying space, things look awfully disconnected and sparse in this setting. And there's a Goldilocks effect that happens in an intermediate phase transition, where if the rate of decay is just right, then the random points exhibit a sort of topological signature, and this is known as the thermodynamic regime. And this is what we'll sort of focus on today. So with this background, statistical invariance is characterized as follows. So we're given a family of probability distributions defined on a Euclidean or sub-Euclidean space X, which contains at least two distinct probability distributions. And we're given some points that are sampled from these distinct probability distributions. And the topological summary that we will focus on is the collection of all Betti numbers. And in a sense, it encodes the topological and the probabilistic information that underlies these random points. And statistical invariance will imply that points sampled from two distinct probability distributions emits identical asymptotic behavior. Or in the parlance of statistics, it means that they are measuring the same population level quantity. So here's a familiar example. So suppose we consider the location family of normal distributions and a summary statistic in the form of the sample mean. Then we know that the sample mean contains enough information to distinguish between two distinct distributions from that belong to this family. However, if we were to look at the scale family of normal distributions, where the parameter set is indexed over the cone of positive definite matrices, then the sample mean essentially contains no parametric information. So as the number of points goes to infinity, if we look at the sample mean, they become almost indistinguishable. So in a similar vein, our objective is to understand the nature of parametric information that is captured by the Betti numbers, and also to see if we can use these topological summaries in a statistical setting where we can distinguish between two distinct distributions, say in a two-sample testing framework. So the assumptions, there are some assumptions on the space on which the probability distributions are defined. If it's a lower dimensional manifold, it has to be compact, we need some differentiable structure, and the probability distributions and their densities have to be sufficiently regular. And these are the standard assumptions in the probabilistic study of these topological summaries. And we'll focus on the Cech complex, but it sort of very naturally carries forward to the Trips complex as well, because we're looking at the behavior in this law of large numbers setting. So, okay, so as the number of samples goes to infinity in the thermodynamic regime, we define by this quantity the thermodynamic limit in the regime as where T is the thermodynamic limit. And this is a statistical functional. And we say that the family of distributions admits Betti equivalence if this thermodynamic limit is identical for all distributions that belong to this family. So if we're given a family of distributions that is parameterized by the set theta, then Betti equivalence implies that the thermodynamic limit that these distributions admit for this family is independent of this parameter theta. And again, in the parlance of statistics, this means that the Betti numbers are asymptotically ancillary to the parameter theta that indexes this family. Okay, so we come to the first result, and before I talk about it, I'll just mention that for the rest of the talk, I'll use this class F and P interchangeably, where F is the family of density functions associated with P, and each one uniquely determines the other. So I'll use them interchangeably. And so we look at a property that distributions need to satisfy that's sufficient in order to guarantee Betti equivalence. So if we're given a family of distributions with the property that the transformation of a random variable under its own density is identically distributed across the family, then this family admits Betti equivalence. So this property is sufficient to characterize distributions that admit Betti equivalence. And the main idea for this result comes from just looking at the functional form for the law of large numbers limit in these papers. And although it doesn't have a closed form solution, it still admits this functional form that guarantees that we can extract this sort of behavior. And I'll talk about this remark towards the end. So invariance also implies invariance for the persistent Betti numbers in the Euler characteristic as well. Okay, so we have some notion of what property these distributions need to admit for them to demonstrate this property of Betti equivalence. So now I'll focus on understanding the structure of these distributions, and more specifically, we look at them from a constructive perspective of how we can construct a family of distributions that satisfy this property. And this sort of sheds more light on the structure of these distributions as well. So the first notion comes through what is called group invariance in statistics. And essentially the setup is that we're given a group whose elements are indexed by this parameter set theta, and they act continuously on the space X on which our probability distributions are defined. If we're given a map T defined on the space X, this map is said to be G invariant if it's constant on the orbits of the group. And it's G maximal invariant if it is constant only on the orbits. So it sort of distinguishes between orbits based on the values it takes. So for a simple example is illustrated over here. So if we given the special orthogonal group acting on the Euclidean plane, then maximal invariant function would naturally be the L2 norm associated with every point in the plane. And I'll also just mention that maximal invariant functions are unique up to injective transformations. And the basic idea of group invariance in statistics is that if we're given some pivotal random variable X, then the action of the elements of the group on this random variable induce a family of random variables whose distributions now depend on the parameter that parameterizes the elements of the group, and so we get a family of probability distributions. And so, whoops. Okay, so the general idea now is that we use the property that we described in the earlier proposition, where we look at the transformation of a random variable under its own density, and so z theta is the new transformed random variable, and the objective is to show that the density of z theta now is a G invariant function. So by imposing this algebraic structure, we can sort of make stronger claims about properties that these distributions need to satisfy for them to also admit Betti equivalence. So this result says that if we're given a family of distributions whose density function takes on the following functional form, where C is just a map from the space X to a space Y, G is a parameterized group of isometries that act on the space Y, and T is a maximal invariant function associated with this group, and C is just any function that ensures that this functional form is a well-defined and valid density function. Then this family of distributions indexed by theta admits Betti equivalence if and only if the following Jacobian constraint is satisfied, that the determinant of the Jacobian of the inverse map of C is a function of the maximal invariant function associated with the group. And I think this is sort of best illustrated through the following example, where we look at a family of distributions defined on the unit square in the Euclidean plane. And the general strategy for verifying that it satisfies Betti equivalence is to make sure that this density satisfies the template that we defined in the previous theorem. So if we consider the special orthogonal group again, whose maximal invariant is given by this, then we can use this map C, which is just the projection, the square of the projection onto its first coordinate, and then express this density in the form that we had earlier. And I forgot to mention that phi over here is the cumulative distribution function associated with the normal distribution. So it's just the CDF of a normal distribution and the inverse CDF. So the density admits this functional form. And to verify that this Jacobian condition is satisfied, you can see that the determinant of the Jacobian for the inverse map is just the product of their individual densities. And this product is basically just a function of its associated maximal invariant function. So it admits Betti equivalence. And this is an illustration of different densities that belong to this family. And each of all of them admit Betti equivalence. Okay, so the next notion comes by preserving what is called the excess mass function. Okay, so if we're given a probability distribution with a density function f, the excess mass function is just the mass assigned to the super level sets associated with the underlying density. So this is a depiction of what the excess mass is measuring. And the reason for considering the excess mass function is that the property that we were looking at so far was this transformation of a random variable under its own density is identically distributed across the family. This property is equivalent to requiring that every distribution within this family admits the same excess mass function. So this is the reason for considering this new perspective.
So we have one question.
Okay.
So SO2 does not map the square into itself.
Yes. So so going back to this example, so the group acts on the space Y, which is the image of this map C that we defined in the previous result over here. So the inverse CDF takes points on the unit square into the Euclidean plane, and the special orthogonal group acts on the Euclidean plane, not the unit square. Is that okay?
So I don't see any follow-up questions. So yes, okay, thanks.
Okay. Okay, so the next tool that we need is this notion of the modular character associated with the measure. And essentially the modular character measures or describes how the measure changes under diffeomorphic transformations as a function of this determinant of the Jacobian associated with this diffeomorphism. And we're sort of essentially borrowing this terminology from the literature in harmonic analysis. And a simple example is if we consider the Lebesgue measure on Euclidean space, then by the simple area formula, the modular character associated with the Lebesgue measure is just the identity map. But we need this additional generality when we look at the decomposition of the Lebesgue measure in spherical coordinates, where we have a surface measure on the spherical shells and a measure on the radial cross section, which has a non-trivial modular character. So this sort of becomes useful over there. And this first result is fairly intuitive. So if we're given a density on a space X, which is a density with respect to a measure nu that has modular character C. So the first property is that this density is the support of this density is contained entirely within the space X. And we're given a collection of diffeomorphisms that act on X in such a way that the image of the support of this density under each of these diffeomorphisms is an almost everywhere disjoint set. Then we can construct this family of distributions that admits Betti equivalence and is indexed by the collection of diffeomorphisms that satisfy this following Jacobian constraint. And again, this is sort of best illustrated through a simple example where we construct so using a density that is defined just on the positive real line, we construct a density on the whole real line using the parameter set indexed on this hyperbolic curve. And this is the general functional form that this density takes. And if we were to look at it in the context of the previous functional form, the maps phi1 and phi2 are essentially scaling points on R plus by a factor of A, and a factor of b and mapping it to the negative real line. And the Jacobian constraint essentially says that it has the values of a and b have to be in such a way that it lies on this hyperbolic curve that parameterizes the set that we look at over here. Okay, so so lastly, this notion of preserving the excess mass is very nicely generalizes to cases where the space on which the distributions are defined admits a smooth fiber bundle structure. So here Z is the base manifold, Y is this canonical fiber space associated with the fiber bundle. And if we now induce a probability measure on the base manifold and a probability measure on the fiber space, we can use these diffeomorphisms phi, which take values on the product of the fiber and the base manifold and take values on the fiber space itself. We can use these maps phi to index a family of density functions that admit Betti equivalence so long as this following Jacobian constraint is satisfied. And you can sort of see that this Jacobian constraint is a natural generalization of the Jacobian constraint that we had in the previous result. And in the interest of time, I'll refrain from talking about specific examples for this, but you can, if you're interested, you can look at our paper on the archive, and we look at examples of distributions on the Hopf bundle or the torus, etc. Okay, so far we've looked at examples, constructive examples of distributions that admit Betti equivalence. On the flip side, let's say you're given a family of distributions. How do you ascertain whether or not it admits Betti equivalence in the sense that we talked about so far? So it's fairly cumbersome to sort of deconstruct the given family of distributions you have and try to fit it into any of the templates that we've described earlier. So the next result is a fairly simple condition that parametric families of distributions must satisfy in order to admit Betti equivalence. So if the gradient of the Lk+1 norm associated with the density is 0 for each value of k lying in the natural numbers, then it admits Betti equivalence. And under some stochastic regularity conditions on the associated densities, it leads to a very interesting geometric constraint that any power of the density function has to be orthogonal to its associated score function. And the score function is a very fundamental tool used in classical parametric statistics, where the zeros of the score function are the maximum likelihood estimators, and the variance of the score function describes the Fisher information, which is a natural Riemannian metric that you have on the manifold of probability distribution. So this is a very interesting geometric constraint that Betti equivalent families must satisfy. Okay, so just to summarize, so we described what this notion of Betti equivalence by requiring the thermodynamic limit is identical across the family of distributions. And then we looked at constructive examples and methods to verify whether a family of distribution admits Betti equivalence. So I'll just close by discussing some natural extensions or implications of this. So the Euler characteristic and the persistent Betti numbers also admit invariance for Betti equivalent families in the thermodynamic limit. So it's easy to see that it holds for the Euler characteristic because it's just the alternating sum of the Betti numbers. But for the persistent Betti numbers, a recent paper by Johann Krebs and Wolfgang Polanek, you can see that the thermodynamic limit of the persistent Betti numbers as well admits the same functional form that guarantees that Betti equivalence holds. Another interesting extension would be to the process level summaries that were recently considered by Awada and Thomas. And interestingly, during the talk last month by Andrew Thomas on AATRN, these process level summaries are just Cadillac functions that lie in Skorohart space by looking at t from 0 to infinity. a question was raised towards the end of the talk whether we can use this we can use the Euler characteristic process as a generalization of the Kolmogorov-Smirnov test for multivariate distributions or distributions supported on manifolds. And it seems unlikely that Betti equivalent families are distinguishable even in the Euler characteristic process in this setting. And then obviously another very interesting extension would be to examine if Betti equivalence has any implications on the persistence diagrams. And this is obviously a much harder problem because the space of persistence diagrams has bounded curvature and non-uniqueness of Frechet means, etc. So it would be interesting to see if there's some sort of an implication that this has on persistence diagrams as well. Okay, so that's the end of my talk. Thank you for listening. And if you're interested, you can find more examples on the paper that we have on the archive. Thank you.
Okay, thank you. So before we get to questions, I would invite everyone to unmute themselves so that we can thank Siddharth for his talk. Okay, so I think we have time for 1 or 2 questions. So feel free to unmute yourself and ask. Everybody is set to mute automatically, or type your questions into the chat window.
May I go ahead and ask a question? This is Gugan here.
Yes, certainly. Go ahead.
So hi Vishwanath, nice talk. Sorry for maybe it may appear to be a very basic question, but what I wanted to know was what is this advantage of beta equivalence? In a sense, if I understand in statistics, one would like to discriminate between 2 distributions, right? So what you are saying is in some sense, these family of distributions cannot be differentiated amongst themselves. Is that correct? And if so, how can one use this beta equivalence? Thank you.
Yeah, so you're absolutely right. So this notion of Betti equivalence is saying that the collection of Betti numbers that we look at is so in a sense Betti numbers are insufficient for us to be able to distinguish between 2 different distributions that lie in the same family. So you won't be able to tell the difference between these distributions if you look at the topological summary in the form of Betti numbers. That's essentially what this notion of Betti equivalence is saying. Does that answer your question?
Yes, thank you.
Okay, and then we have 1 more question from the audience. Are there any convergence rates for these limits?
So as far as I'm aware, I don't think there are convergence rates for the law of large numbers that we're looking at. But I could be wrong because I think there are some more recent works where they have more advanced concentration inequalities that probably guarantee convergence rates, but I am not personally aware of the convergence rates.